In this video, we're going to be doing some practice problems for Unit 8 Fluids of AP Physics 1. So let's say a tank is open to the atmosphere and filled with water. At depth h, what is the absolute pressure? So we have the hydrostatic pressure equation, which states that the pressure is equal to the pressure that you have at the surface plus rho gh. And since we know that the tank is going to be open to the atmosphere, we can say that the pressure is currently at equilibrium with the atmosphere, and since it exits into the atmosphere, it's going to take that same atmospheric pressure. Therefore, our pressure at the surface is going to be equal to the pressure that is atmospheric. Therefore, we could just say that our hydrostatic pressure, aka our absolute pressure, is going to be our atmospheric pressure plus our rho gh, which leaves us with option B. At a depth of 10 meters in the water, the gauge pressure is what? Well, our gauge pressure is going to be our pressure that is due to the fluid only. And this is equal to rho gh, which is our fluid. Density of our fluid, the height below surface, and g. So our gauge pressure is going to exclude our atmospheric. We're only looking at the fluid's contribution, which is why our answer is B. Water exits a whole 5 meters below the surface. The exit speed is closest to what? So, if it's 5 meters below, this is 5 meters, and let's say the surface of our water is up here. The water is going to exit in projectile motion outwards, and it's not asked, but it will travel a range of delta x. So, Torricelli's theorem states that your exit speed is equal to the root of 2gh. And plugging this in, we have 2 times 9.8 times 5, which is approximately 9.9 meters per second. So your answer for this is going to be basically 10. So the fluid is going to behave like it fell 5 meters under gravity, which is why we get that speed near 10 meters per second. Now, a tank is 12 meters tall. A hole is located 4 meters above the bottom. So this is 4 meters. The entire tank is 12 meters. What value of h should be used? So they're referring to what value of h you should use when you're using Torricelli's theorem, which is v is equal to the root of 2gh. So in this equation, it's a bit unclear what h is if you just see it. But this is important for you to know the difference. This h is going to be the distance from the surface to hole. And some people might get confused because they think that because the hole is here and then the water goes out like this, they know that the water, once it exits out the hole, it's going to act like projectile motion. However, the height that you're going to use is not going to be this y max height of the projectile motion. We're actually looking at how water travels from the surface of where it's at. So the water is going to be from the top of the tank, correct? And then the water is going to travel downwards to the point of the hole and then travel out. So that's why we're finding that exit speed. So therefore, because we are finding that height, the actual height that we're going to be interested in is actually 8 meters, which we get from our 12 meters minus our 4 meters. So we would use 8 meters in this equation, and we'd have v is equal to the root of 2 times g times 8. And 8 is our answer. So water flows through a pipe that narrows. If the area decreases, what happens to the velocity? So this is referring to our continuity equation. In continuity, we have AV in one area is equal to A2 V2 in another area. And this is because this entire equation is going to be set constant. So if we have that our area on one side decreases, our velocity is going to have to increase for us to maintain the constant value of AV. Because if you have 2 times 4, you would have to make your value 4 times 2 in order to stay equal to 8, correct? So if you increase one, you have to decrease the other, which is why A and V are going to be inversely related on one side of the equation. So if our area decreases, our velocity has to increase. So a fluid must move faster through a smaller area to conserve mass. if the radius of a pipe is halved, velocity changes by what? So we know that area of a pipe, we're typically going to have a circular pipe. And this is the formula for the area of a circle, which is pi r squared. So we know that our area nu is going to be equal to 1 over 4a if we have our radius. Because we have pi times 1 over 2 squared. And that 1 squared and then 2 squared gives us 1 over 4. That's the ratio. So then we can look at our continuity equation. In continuity, we have a1v1 is equal to a2v2. So v2 would be equal to the ratio of a1 over a2 times v1, which is equal to 4v1. Therefore, our answer is B. So, if area decreases by 4 times, that means that our velocity is going to increase by 4 times. Now, in a horizontal pipe, our fluid speeds up. What happens to the pressure? So we're going to use Bernoulli's equation. And we are going to have a horizontal pipe. So we can imagine that this is our pipe, right? And it is always going to stay at the same height, which is why we can call it a horizontal pipe. When we have Bernoulli's equation horizontal, we have that our pressure plus 1/2 of rho v squared is going to be equal to something that is constant. So if we know that it speeds up, well, speed is going to refer to velocity. And here velocity is going to be squared. So that means that if we're increasing velocity squared, that means that you're going to have to decrease your pressure. Because again, if you have to increase one value on one side, then you have to decrease the other value in order to maintain the state of being constant and equal to the other side. So our answer is that our pressure is going to decrease. So again, high speed means that you have increased kinetic energy. And then increased kinetic energy means that our pressure energy has to decrease to conserve energy, because we have our conservation of energy, which is where we get that constant Bernoulli. Now, water flows upward in a pipe and slows down. What happens to the pressure? Well, again, we're going to use Bernoulli. Since we are moving up, that means that you're going to have a height that increases and then you're going to have a v that decreases. And these both are going to affect your pressure. And what this is going to do to your pressure is that your pressure will increase. We can see this in our equation. P plus 1/2 rho v squared plus rho gh is going to be equal to something that is constant. So if you increase your height, that's going to scale this up. And if you decrease your v, that's going to scale that down. So our pressure is going to increase here, because both of these effects will just increase our pressure. So as our fluid slows down and also rises upward, we have to increase the pressure to conserve our total kinetic energy. So this is why our answer will be A. Now an object is going to float in water. The buoyant force is going to equal to what? Well, here's our water. We're going to have, it's at the state of floating. So we have a buoyant force that's up, and then we have a weight force equal to the force of gravity pointing downwards. Now, using Archimedes' principle, we know that our buoyant force is going to be equal to the weight of our displaced fluid. And our weight of displaced fluid is equal to mg. So buoyant force is just equal to mg. So that's just going to be B. So for floating objects, our buoyant force equals both the weight of the object and also the weight of the displaced fluid. So those are going to be equal. Now an object with a density of 0.6 density of water floats. So we want to find what the fraction submerged is. So there's this ratio that we always use in order to find the fraction that is submerged, which is V submerged over the volume is equal to the density of the object over the density of the fluid. And we know that we have this ratio here. This is going to be 0.6. So the fraction submerged is equal to this ratio, and that's how we got that, 0.6. Now for our next question, we have an object is fully submerged but not touching anything. The buoyant force depends on what? Well, we have Archimedes' principle again. The principle states that our buoyant force is equal to the density of our fluid times our gravitational constant times the volume that we displaced. Now, what can we think about here? So we know that the density of our fluid is still submerged. So we know that this is still going to be something that is constant, right? We know that as long as you're on Earth, this is also going to be something that's constant. Now, what about our volume displaced? Well, volume displaced, we know that this is going to vary based on the volume of the object, of course. Now, we have to check our dependence on depth. What here do we know would change if we changed our depth? Well, we know that we have pressure, and this is equal to our pressure initial plus rho GH. So we know that pressure is going to increase if you increase your depth, H. And we know that the pressure difference, your delta P, when you're looking at top versus bottom, is still going to be our buoyant force, which is equal to rho G volume. So we know that that means that our buoyant force, FB, is going to be independent of depth, since V doesn't involve H, our depth. So FB is going to be B. It's independent of the depth. Now, an object floats between oil and water, which determines how much of the object is in each fluid. So we have our case here, and it's going to be floating between oil and water. Say we have our oil down here and our water up here, and it's teetering right now. Well, we have to think about our vertical equilibrium. So if it's floating currently, we're going to assume that it's in vertical equilibrium. Therefore, the sum of the vertical forces is going to equal to 0, because the acceleration in the vertical direction is going to equal to 0. So then, if you have your buoyant force from the water plus the buoyant force caused by the oil, this is going to equal to the mass times the gravity. Now, all you're going to do is substitute in your Archimedes principle. Your FB is equal to the density of the fluid times G times the volume displaced for buoyant force of the water and buoyant force of the oil. So that's going to be density of the water, G, V of the water, plus density of the oil, G, V initial, V oil, I mean. And this is going to be equal to the density of the B, G, V, which we'll call just B as our block. So now, after this, we can see that each term has a G, right? So you can cancel this out, and we're left with this. So what can we see? We're asked what determines how much is in each fluid. Our options are height of the fluids, density, pressure at the bottom, and volume of the tanks. So we see that we have no height of the water, and there's also no height of the oil, and there's no pressure terms inside of our equation. So that means we can rule out the height of the fluids and also pressure. So our answer is going to be B, because the volume of the tank is going to be something else. Because you don't have to not necessarily take up the entire tank. The volume of the tank is irrelevant, because we could have a massive tank, but we could only fill it up to here. So why does the volume of the entire tank matter? It doesn't. So a water jet hits a wall and it stops. The force depends on what? Well, we have to use our momentum principle. So we know that force is going to be equal to derivative of momentum. If you've seen this introduction, and we also know, you don't have to necessarily know this, but it's good to know for AP Physics 1. We know that our mass flow rate, we can write it here M is equal to the density times AV. And now we're going to have a change in momentum because our fluid is going to go from V to 0. So that means your change in V is equal to 0. Now what about our force? That's equal to mv. And that's going to be density AV squared. So here, we're going to see that our force is going to depend on how much mass hits per second and also how fast it was how fast it was moving. So that's your mass per second and also how fast it's moving. Water flows from a wide pipe to a narrow pipe. Which of the following is going to be true? So let's say we have our wide pipe here, and then we shrink to this smaller pipe over here. This is going to be A1, and this is going to be A2, and let's call this a circular pipe. Well, since we know that the water is going to flow from one area to the next, we can use continuity, which states that A1V1 is equal to A2V2. So that means if you increase your area, right, that's going to have your, or let's say if you decrease your area, I mean, as we go from this large section to the small section, right? So this is a large A, this is a low A, right? So as you decrease your A, as you go into the second section, you're going to have to increase your V. Now, what about in Bernoulli, what we saw earlier, right? We already know that Bernoulli for our horizontal pipe, which is what we have here, because the height is going to stay the same, so our UG term is going to cancel out since we know that UG is equal to MGH, and if the height, your delta height, mg delta height, that's going to be equal to 0. So that means that's why your UG terms will cancel out on both sides of your Bernoulli equation. You're going to have that your pressure plus 1/2 rho v squared, which is that's your pressure term. This is your kinetic energy term again. And we know that this is going to be something that's going to be held constant. Well, if we see that if this has to stay constant, right? If our pressure and our 1/2 rho v squared, our sum of that has to stay constant. And if we increase the velocity, that means that you're going to have to decrease your pressure because that velocity is going to make this entire term here increase, right? So that means that the only thing that we can do if we increase one component of it, we have to decrease the other component of it in order to stay the same. So that's why we're going to have that our speed is going to increase and our pressure is going to decrease. Again, because of the idea of energy conservation. Now we're asked what the pressure, so the pressure at a given depth depends on what? Well, here we can again use our hydrostatic equation. Our pressure is going to equal to P initial plus rho GH. So let's see what our variables are. So this is our equation for our pressure at a given depth, right? So what variables do we have here? We have our rho density, of course, our H depth, and we have our gravitational constant. So what does it not depend on? Well, here we're given options of shape, but shape of the container is not even in the equation. Neither is our volume of the fluid, nor is our area, our surface area. That's not here. So we can see clearly that only our depth and density are in our equation. Now, for question 16, if the surface pressure increases, what's going to happen to the exit speed? Well, we can use our generalized equation. Our volume, or our V speed, exit speed, is equal to the root of 2 times P1 minus P2 divided by our density plus 2 times GH. And if we have an increase in our pressure 1, if we increase pressure 1, the specific part of our equation is going to be this P1 minus P2. So we're going to have P1 minus P2. This component is going to increase as well. And if you increase this component, then you're going to have 2 times that component divided by a density. So 2 will stay the same. Whatever you're going to be dividing by a density of is going to stay the same. And then Everything else is going to stay constant. So like, let's look at this. That's going to be the same, this is going to be the same, this is going to be the same. So we can see that if you increase that, it's in the numerator with our v. So those two are going to scale together, be directly proportional. So v is directly proportional to the square root of p1 minus p2. And this is going to mean that your v is going to increase as well. So greater pressure difference is going to, so this is your pressure difference. That's going to give you a higher energy, right? If you have a greater drop in pressure, that's going to give you more energy. So that is going to give you a higher speed, more potential for it to be turned into kinetic energy, and kinetic energy has 1/2 mv squared, and that is your speed, right? So an object is lowered deeper into the water. Our buoyant force is what? So if we're going deeper in the water, so our water here, we have our object and it's going down. So we have to see what is our buoyant force formula. Again, from Archimedes Principle, it's going to be rho g volume displaced. Now, what are our variables? So here, our volume displaced is going to stay the same, right? Because our object is still going to be the object. As you push it down into the water, it's still going to displace the same amount of water and push that water around it as it makes room for it to like go down. Our g is also going to stay the same as long as you're in Earth. And your rho is going to be the same because you still have water, right? So we know that pressure, right, is going to increase if you have an increase in your depth. But here we have a top force and we also have a bottom force. So they are both going to increase for our object. So if they both increase, that means that their difference will stay the same. They're going to act in opposite directions of one another. So that means that our answer is going to stay the same. And we can also see this again from just looking at Archimedes' principle. Nothing in our buoyant force formula is going to change. So now Torricelli's theorem comes from what? Well, if you remember Torricelli's theorem, we have at first our Bernoulli's equation, which is pressure plus 1/2 rho v squared plus rho gh is going to be something that is constant. And this is energy conservation. So Torricelli was a specific case where v is equal to the root of 2gh, where we had our fluid of water, we have gravity and we have our h here. And that is going to be B. That's our conservation of energy. Now, pressure at the bottom of an oil water system, which is, let's say, down here. We have our water here, and we have our oil down here of this system, is going to be what? So this is going to be what we have to add the pressures by the layers. So at the top, we're going to have atmospheric. Then we're going to have oil. I don't know why I wrote that. So let's actually put oil at the top because it floats. And then we're going to have water. You have to remember that air is still a fluid. So by layer, we have pressure is going to be the sum of all these pressures. Atmospheric plus our oil, GH, depth, plus our density, water, GH, water. So our pressure is going to be the sum of all these layers. So that's because each of the fluid is going to contribute its own pressure. So that's why we have to add them. Now we have a floating object remains at an interface while the water level drops. The fraction submerged in the water is going to be what? Well, as our water level drops, we're going to have to think of this with buoyancy, right? So our buoyancy equation, we're going to have density water plus V water plus density oil plus V oil is equal to density of the block V. So we are going to see that if we draw this out for our problem, we're going to have the volume is going to be that V. Or we're going to have the V, and then we're going to have volume of the water. So we have to find V oil by finding the difference of V minus V of the water. So then if we have that for V oil, then we can substitute that into our equation. We're going to have density water, V water, plus density oil, V minus V water is equal to the density block V. Now here, all you're going to do is just solve. So you can distribute those. You have density water, V water, plus density oil, V, minus density oil, V water, is equal to density block V. Take this to the side. We have V water, density water, minus density oil, is equal to V density block minus density oil. So V water is going to equal to V times density of your block minus the density of your oil, divided by the density of the water minus density of the oil. And what we see here is the fraction submerged in water is going to be what? Well, here we can see that you're going to have no H water. So you have no height terms in this equation. Now, that means that our answer is going to stay the same. Because if our water level drops, that means that your depth is going to drop, right? So our fraction submerged of V water, that's only going to depend on the densities. So it doesn't change as long as the object remains at the interface with these fluids that are in the interface having and containing the same densities. So